Far from shore, survival on an oil platform hinges not on willpower, but on layers of engineered backup, N+1 systems designed so that even a single breakdown will not endanger lives. When those layers start to unravel, every interconnection, water, power, and air becomes a point of potential failure. Few ever see how rapidly safety margins can disappear, or why a single missed detail can trigger a chain reaction at sea. So how do these platforms really keep people alive? And what happens when they do not? An offshore platform is a closed ecosystem, engineered so that every basic need, water, power, air, and waste, circulates through a network of machines and pipes. The physical layout reflects this logic. Deep within the hull, seawater is drawn through intake strainers, then pushed to the desalination train. Here, high-pressure pumps force salt water through membranes, producing the fresh water that supplies every tap, shower, and fire hose on board. If the water maker's slow, even for a few hours, the entire platform feels it. Storage tanks hold a buffer, but not enough for days. Beside the water plant sits the sewage treatment unit. Every toilet flush and drain cycles through this system, which breaks down waste and returns clean effluent to the sea. The pumps and aerators rely on a steady electrical supply. Any interruption can back up the entire process, creating a chain reaction that is felt in living quarters and control rooms alike. Above these utilities, the generator switchboard forms the backbone of the platform's power. Multiple diesel generators run in parallel, each capable of carrying the critical load if one fails. Power flows to every system: lights, HVAC, water makers, and control panels. Switchgear and automatic transfer panels stand ready to isolate faults and keep at least one path open even during a blackout. Air is managed by a central HVAC system, filtering and circulating to maintain pressure and remove dangerous gases. Each component is physically separated and cross-tied, so a single failure does not bring everything down. But every connection is a potential point of weakness, and every shortcut in one system can ripple across the rest. Redundancy. On an offshore platform is not an abstract idea. It is measured, calculated, and built into every critical system. For electrical power, the standard is N+1, which means one more generator than the maximum expected load. If the platform needs 3 generators to run at full capacity, a 4th stands by, ready to start automatically within seconds if one fails. Essential systems such as lights, communications, fire pumps, and water makers are wired to isolated emergency buses. These buses are physically separated from the main grid, shielded by fireproof bulkheads, and supplied by independent cabling. In a blackout, emergency power is guaranteed for life-critical loads, even if the main switchboard is lost. Reserve margins are not left to chance. Industry guidelines require that the emergency bus can support all essential services at a fixed fraction of their rated demand, often 100% for fire pumps, 50% for HVAC, and 30% for general lighting. Water storage is sized for at least 24 hours of normal use, with a further 12 hours in reserve. Sewage holding tanks are calculated to buffer a full day's waste if pumps fail. Each system is cross-tied to its neighbor, with isolation valves and breakers that can split the network in seconds. This compartmentalization means a fault in one area does not automatically cascade across the platform. Redundancy is not infinite. The numbers are precise: 1 spare, 1 buffer, 1 backup circuit. If a generator is offline for maintenance, or if a valve is left closed after a test, the margin shrinks. The platform's safety depends on these engineered limits holding firm, until they do not. At 8 in the morning on day 0, a seawater strainer in the desalination loop showed rising differential pressure after a week of heavy silt in the intake. Maintenance flagged it for cleaning, but with production targets looming, the job was deferred to day 2. The decision was logged, the bypass noted as temporary, By midday on day 1, the main desalination train tripped on low flow. Salinity alarms lit the SCADA screens, and the standby unit failed to start because an isolation valve, left closed from a prior bypass, blocked the transfer. With freshwater production halted, rationing began. Cleaning cycles for equipment were cut, and the sewage plant shifted to reduced duty mode. By early day 2, solids and grease built up in the waste system, slowing pumps and increasing electrical draw. The SCADA trend showed a steady climb in load on the auxiliary bus. On day 3 at 10:10 at night, a scheduled heater shift pushed the main generator to its limit. The overload tripped the unit, dropping the platform to a single generator. Fire pump reserve fell to 80%. The maintenance supervisor recalled that they had the bypass documented as temporary, but the valve status was not re-verified after use. That was all it took for the margin to collapse. What began as a minor deferral in one system had, in 3 days, eroded the platform's reserve across water, waste, and power, exposing the fragility of the whole ecosystem. At 3 minutes 15 seconds, a fault in the auxiliary lube oil pump forced a compressor shutdown. The main generator, already near its upper load limit, tried to absorb the sudden shift. Within seconds, protective relays tripped, dropping the platform onto emergency power. The automatic transfer sequence was supposed to bring a second generator online, but a corroded breaker on the hot standby unit blocked the transfer. Only the emergency generator remained, forced to shed all non-essential loads. Lights flickered across the accommodation block as HVAC, the galley, and several process circuits went dark. The fire pump system, which depends on a stable power supply to maintain pressure for deluge and hydrants, now operated with a margin cut to 60%. Operators scrambled to stabilize the electrical network, manually shedding loads to keep core safety systems alive. Maintenance records later revealed the breaker corrosion had been flagged 2 months earlier, but the inspection was postponed due to spares shortages. In less than 15 minutes, a single auxiliary pump failure had exposed how quickly engineered redundancy can erode, leaving critical safety systems balanced on a single point of failure. At 4 p.m., a technician initiated a planned calibration on a fixed gas detector in the compressor module. The only spare unit was already out of service, so the detector was bypassed under a permit to work that authorized a maximum duration of 12 hours. The permit required a roving patrol to check the area every 2 hours, with handover to the incoming shift at midnight. Overnight, the shift rotation blurred the timeline. The outgoing crew failed to update the permit register, and the bypass remained in place 6 hours past the authorized limit. No entry appeared in the patrol log after 4 a.m. At 5:45 a.m., the compressor was restarted for a warm-up cycle, releasing a short-lived pocket of hydrogen sulfide. With the detector still bypassed, the zone alarm was delayed by 18 minutes, enough to trigger a muster before the control room could issue a targeted shutdown. The redacted permit, later reviewed by regulators, showed the original 12-hour cap and missing handover initials. A simple lapse in paperwork, compounded by fatigue and routine, had turned a procedural control into a real hazard. Emergency drills on offshore platforms run with the precision of a scheduled operation. Crews muster at assigned stations, lifeboats are lowered, and checklists tick off each required step. These exercises confirm that escape routes are clear and that everyone knows their role. But the conditions are always controlled: daylight, full power, reliable communications. After action reviews often highlight smooth execution, yet rarely address what happens when the script breaks. During low visibility or simulated power loss tests, response times slow by up to 40%. Muster tracking systems, which can cut evacuation times by 70% in theory, depend on working sensors and open lines. Lifeboat systems are rated to evacuate over 150 people in 10 minutes from 80 meters above the sea, but only if weather and machinery cooperate. An HSE officer says that our drills prove the plan, but real emergencies find the gaps we never rehearsed. Routine success can mask just how thin the margin is when one system fails. Every decision offshore is shadowed by the weather. Swell and salt spray do more than rattle the walkways. They double corrosion rates on exposed equipment, forcing maintenance teams into a race against the elements. On paper, there is always a window to shut down and repair, but forecasts shift, and cost pressure narrows those windows. Operations managers describe the tension as a constant negotiation. Delay for one more load, or halt before the next front moves in. In high swell, the margin for error shrinks. Fatigue compounds, especially as rotations stretch past the third week. Human factors specialists track the trend. After just a few rotations offshore, half the crew will not return. Attrition climbs as monotony dulls attention, and the line between routine and risk blurs. In interviews, managers admit that decision windows compress under both weather and turnover, making it harder to hold the line on safety when the sea and the schedule close in together. Every system offshore has a breaking point, and no checklist can erase that risk. As oil rigs age and storms grow harsher, the line between routine and disaster narrows. The margin for error is shrinking. Survival at sea demands constant vigilance, not comfort. Thank you for watching.